Hello, my presentation is solving the lid-driven cavity using the stream function vorticity method. We are all very familiar with the lid-driven cavity at this point. It is one of the most common benchmarks for validating numerical methods. I wanted to use this problem with known solutions to test my ability to teach myself the stream function vorticity method and how to implement it. The main motivation for this method is that you can eliminate the pressure term. This means you only need two coupled equations for stream function and vorticity instead of u, v, and pressure. Next, it significantly reduces the computational time required. It also provides rotational motion information with vorticity, but the main downside is it cannot be extended to 3D. Now I'm going to go through a very quick derivation of the stream function vorticity method. First, the vorticity is defined as the curl of the velocity. In 2D, this is defined as equation 2. Next, we will convert the momentum and continuity equations into equations consisting of the stream function and vorticity. If we take the curl of the momentum equation, we get the third equation, which is the vorticity transport equation. From here, the continuity equation, we can define the u and v velocities as seen in equation 4 and 5. Plugging this into equation 2, we get equation 6, which is the Poisson equation. From here, our system is defined from equations 3 and 6. The implementation goes as follows. First, you solve the vorticity transport equation at interior grids. Then you calculate the stream function using the Poisson equation iteratively using Gauss-Seidel. Then you find u and v using the equations you see on the right here. Next, you solve the boundary conditions and then check for convergence. Now we are going to look at the boundary conditions. Here's an equation for the left wall, for example. First, we start with the Taylor series for the stream function, and we get equation 1. From here, we're going to plug in two values. The first is from equation 2 that we saw in the last slide, and the next is derived from equation 3. If you apply the boundary conditions to equation 3, you get equation 4. Plugging in equation 2 and 4 into equation 1, you get equation 5, which defines the left wall boundary. As you can see in this, the v component for the left wall is 0, and that will be the cases for the left, right, and bottom wall, but of course on the top wall, there will be a velocity here. Here are the streamline plots for Reynolds number 100, 400, and 1000 at n value 129. As you can see, this is what we expect with the center vorticity moving to the center as inertial effects become larger relative to viscous effects, and you can see that the secondary and tertiary vorticities become larger as Reynolds number increases as well. Here are the results from the u and v component centerline velocities. As you can see, they closely map to the results from the GIA paper for Reynolds number 100 and 400 with an n value of 129. The average convergence rate for the u component at Reynolds number 100 was 1.99. For the v component, it was 2.02. The u component at Reynolds number 400 was 1.70, and for the v component, it was 1.74. As you can see, as the Reynolds number increases, the convergence rate decreases. The theoretical convergence rate is 2.0 using the central difference discretization. This is the opposite trend that we see in other methods like Lattice-Boltzmann and the projection method, where the convergence rate would actually increase with larger Reynolds number. From my understanding, with this method, with larger Reynolds number, it becomes less accurate because of how the boundary conditions for vorticity are defined, as they are not explicitly defined like the velocity boundary conditions are in these other methods. Here are some other interesting results I got from the convergence rate. As you can see in the graph on the left for the stream function vorticity, the far left dots are when I compared between grids 13 and 25, the middle dots are when I compared between grids 13 and 49, and the far right dots are when I compared from 25 to 49. And as you can see, as you increase between the average grid size for what you compare between, the convergence rate would increase. This is not what you saw in any of the homeworks for the other methods, as you can see on the right-hand grid. I'm not exactly sure from the readings I did why this was the case, but I found these results to be very interesting and worth noting. Here are my references, and thank you all for listening.